Hi kids, it's black holes number 3 this time. I don't know what I need to say. There's so much stuff I could say right now. There's a lot. I'm gonna go with the things black holes do when they hit stuff. So if a neutron star hits a black hole, you get a big boom. If a neutron star hits a neutron star, you get a big boom. They're both called hypernovas. Hypernovas are just this big explosion, bigger than a supernova. Not the most deadly thing in the universe. It's the second most deadly thing in the universe. So you can have black holes colliding with things, and if it happens to be a neutron star, you get a big boom. If a black hole collides with a black hole, on the other hand, I don't know what happens. There's no light, so we don't know what goes on. I mean, it's this big. Remember how big a black hole is? They're this big, and so if two of those hit, boop, right? This is a little squeaky noise. I don't know. I mean, I have no idea. And so you get black holes combining together. You end up with supermassive black holes. The black hole in the middle of the Milky Way galaxy is a combination of multiple black holes. It is supermassive. It is not the largest by far. It is thousands of times bigger than the sun, but there are some that are billions of times bigger than the sun. And so you get these supermassive black holes by combining black holes together. And they usually end up in the middle of a galaxy. And then if a black hole is not colliding with a star, but it's being orbited by that star, and the black hole is stealing material from that star, but it tries to eat too much, it belches. It's called a gamma ray burst. And gamma ray bursters are everywhere, constantly, all the time. The Milky Way, we ran out of stars in the very center of the galaxy. Instead of having a bunch of stars close to our black hole, they're going around it very quickly, far away. And so it's not choking on that material anymore. It's not belching up those gamma rays anymore. But what happens is a bunch of matter tries to get into the black hole all at once. It can't happen. There's not enough space. The singularity, it has no width and height, and there's no room for all that stuff to go in. And so the electrons get really agitated up at the event horizon, and they start calming down, releasing lots of gamma rays. Well, when a whole bunch of them do it all at once, you get a gamma ray burst. A gamma ray burst can obliterate a solar system all at once, the entire solar system. They're that big, they're that powerful. They just go boom. And we thought, we didn't have any idea they existed until we put a satellite up to spy on the Soviets. And what we did was we put a satellite up trying to detect nuclear bomb tests to find out how advanced the other countries' nuclear test programs were. And we discovered that there were thousands of bursts of gamma rays going off every day. Just gamma ray burst after gamma ray burst after gamma ray burst. And we thought, the Soviets are testing nuclear weapons in space because they were all coming from outer space. So they turned the satellite around to look at the gamma ray bursts, and there's one there, and 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 there. They're everywhere. They're all over every core of every galaxy that's young. Now, the Andromeda Galaxy and the Milky Way Galaxy, they're old enough that it's not happening. And the Magellanic Clouds, they're young enough that it's not happening. But all these galaxies out there, billions of galaxies out there, and they're gamma ray bursting. Trying to eat too much material, the material creates all this friction, and boom, material just shoots out, gamma rays just shoot out through the magnetic poles, the magnetic north and south pole of the black hole, and anything in the path is just gone. It will be disintegrated. That's how much energy is coming out of these things. They are more powerful than supernovas and hypernovas, but not visible because it's a gamma ray spectrum. We can't see it happening. So you got visible light, X-rays, gamma rays, cosmic rays. Cosmic rays being the most dangerous, the highest frequency. Gamma rays are incredibly high frequency and invisible. So anyway, that's black holes, kind of the summary of black holes, kind of the end of it. I don't know, there's a lot I could say about black holes, but I really need to move on to solar systems. And so I'm going to go ahead and make this our solar system presentation as well. This is the nebular theory for solar system formation. You remember nebulas compress and turn into little nodules. Those little nodules are called protostars. There's 8, 10, 12 protostars per little nodule. Little nodules are like a light year across. You get 8, 10, 12 protostars in there. Those protostars ignite and spread apart, moving away from each other, and create their own individual solar systems. But how does the solar system start from that? So you have you got a big gas cloud. It just made protostars turn into stars. Your stellar nursery has tons of gas and dust, not dust and gas and dust, in that order. And you get the gas and dust swirling around these protostars. The protostar ignites, most of the gas and dust is pushed away, but the heavy particles stay near the protostar, or the new star that just ignited. And the material that's rocky and solid stays near the star, and the material that's gassy and fluffy gets pushed. It's so fluffy I could die. It gets pushed away from, I'm gonna have to put that unicorn up there. It gets pushed away from the star, and so your solid rocky planets are near the star: Mercury, Venus, Earth, Mars. The asteroid belt, which could have formed a planet, but it's in just the wrong spot to form a planet because the gravitation pull of the sun and the pull of Jupiter, it just can't get together. But it would be a rocky planet if it was a planet. And then the gassy planets: Jupiter, Saturn, Uranus, Neptune, and then random rocky bodies outside that, which includes Pluto, the Kuiper Belt, and the Oort cloud, which are all asteroids and comets. And so nebular theory of solar system formation states that after a star ignites, its gas and dust surrounding it will form a disk called an accretion disk. You need to know the word accretion disk. It's on the test quiz, whatever I give you this week. Accretion disk forms protoplanetary rings. The protoplanetary rings, I'm going to try and put an image of protoplanetary rings somewhere in this vicinity right here. Protoplanetary rings are going to form planets, except where the asteroid belt formed. That it didn't quite form a planet because Jupiter is trying to pull the material to Jupiter, but the sun is trying to pull the material to the sun, so you get asteroids instead of a planet. Then the light materials move out, so your gas giants form farther from the sun or star than the rocky planets. So your terrestrial planets are rocky. Terrestrial is rocky planets. Jovian planets are like Jupiter. That's what Jovian means, like Jupiter. They're gassy planets. They're gas giants. And so inside near the sun, in the Goldilocks zone, your rocky planets. In the gassy frozen bodies zone, your giant gas giant planets. And so that's basically the nebular theory for solar system formation. What you have outside of in my classroom, if you remember Tarantulan on the ceiling, what you have outside of Pluto's orbit is the Kuiper Belt. Pluto spends some of its time in the Kuiper Belt and some of its time inside Neptune's orbit, which is the reason Pluto isn't its own planet anymore, is because it crosses Neptune's orbit every 200 years or so. That's the definition of dwarf planet. It doesn't have its own orbit. It has to share its orbit with something else part of the time. And so Pluto is out there with the rocky bodies in the Kuiper Belt about 100 years out of every 400 years that it takes to go around the sun. And then you've got a bunch of asteroids in there. And then in the Oort cloud, beyond the Kuiper Belt, surrounding the solar system, it's a sphere around the whole solar system. Is not the outside of the solar system, it's part of the solar system, is the Oort cloud. The Oort cloud has comets, icy bodies, frozen water, frozen alcohol, frozen amino acids, frozen methane. We landed a probe on a comet that went by one time, and alcohol, amino acids, and lots and lots and lots of water and methane ice. And so all these frozen things out there past Pluto's orbit. And so that's what you get. You got your rocky planets, your gassy planets, and your leftover bits, mostly water, iron, and silica. Lots and lots of silica out there. So everything that the solar system is made out of, everything the Earth is made out of, is out there floating around, including amino acids, which lead to proteins which can create life. Might not create life, but they can create life. And so there's your kind of your nebular theory of solar system formation. You got to remember, protostar forms, accretion disk forms around that, it heats up. If you forget, you guys have been using bad answer keys off the internet. When the disk forms, yes, it flattens out. That's the answer you all copied off the internet. No, it heats up. Without that heat, there is no life on Earth. The heat is key. When the planets heat up, they get a molten core and a solid surface. If they're close to the sun and their rocky bodies, a molten core with a solid surface. Without the molten core, all life dies. Mars has a frozen core, not molten anymore. It wasn't big enough to keep the core molten. And so all life that could have been on Mars is now gone. It might have had life. It might have had bacterial life. We haven't found it yet, but we're looking. If it did, it died when the core froze. So without the heat of accretion, life does not exist because planets cannot be warm enough, and they cannot make a magnetic field that protects that planet from the Earth, from the sun's radiation. So the Earth has a radioactive barrier, an electromagnetic barrier that pushes radiation away from the Earth. The sun would just bake us if we didn't have that. The core of the Earth is solid with a liquid core around it, and the way they rotate together creates a magnetic field, protects the Earth from the sun's radiation, which allows us to have an atmosphere. Mars froze in the middle. Its atmosphere was blasted off. Has a very thin atmosphere with lots of dust storms, that's it. No breathable atmosphere, and the pressure there is way lower than Earth. Obviously, Venus still has its magnetic field because it has a massive, massive atmosphere, 95 times as heavy as our atmosphere. Imagine the air on you pushing down with 14 pounds of pressure. Yeah, on Venus it would be 95 times 14, I don't know, 130 something pounds of pressure from every inch on your body would just squash you flat. So Venus obviously still has a magnetic field maintaining its atmosphere. So you've got to know the accretion disk heats up as it flattens, and it makes the rocky bodies warm enough to have a molten core, which allows it to have a magnetic field. You got to know that part. I'm not sure what else I want to talk about for that. Let's call that good for now, and I'll get some more done next week.